Well, next up is our finalist for robotics and automation category, AstroAnt, a miniature symbiotic robot serving on the outside surfaces of spacecraft, rovers, and landers for inspection and diagnostic tasks. And we have with us Feng Liu to present his team's idea.
Cool, thank you from MIT Media Lab, and my presentation is AstroAnt. Traditionally, in our space, we normally rely on like a bulky robotic systems, like the big robotic arm or astronaut, to do some inspection missions for spacecraft, like the International Space Station. But these approaches are highly costly, highly risky, and they cannot reach to hard to reach, like confined and complex small spaces. Small robotics, they can provide very good functional flexibility, and also they can access to very confined space. And the project I'm showing here is called the Robo. It's a tiny robot like this with magnetic wheels, and with another pair of magnetic wheels on the other side of the fabric. It can pinch the fabric in between and move on your clothing and build an on-body sensor network on your clothing. So this inspires us because a lot of the spacecraft, like the International Space Station, is also covered by a layer of fabric called better clothes for protection. So we can extend the applications of such tiny robots to the space and build on-body sensor networks for spacecraft, rovers, landers, and do some inspection sensing from the outside, and use the data to help with monitoring the performance of the mother spacecraft. And this robot we called the AstroAnt. To validate this idea, I designed two different models of the AstroAnt. This is the model 1. It's a tiny robot with magnetic wheels. It can work on ferromagnetic surfaces and also fabric. And the Model 1 is mainly used to test the mobility of such mechanism in microgravity environment. And with the support from NASA Tech Flights program, we conducted multiple parabolic flights to test the mobility of such a design on different materials, including like a rough surface, sandpaper, better clothes, of course, and aluminum with magnetic paint, and also steel. They all showed very good mobility and obstacle overcoming capability in microgravity environment. And the Model 2 is like this. It's a bigger and more powerful design, longer battery life, and also it's a modular design. It can carry different sensor payloads based on what kind of data we are interested. And we also conducted parabolic flights for testing the sensing capability of this kind of design in microgravity environment. It can carry different sensor payload for different data collection, including, for example, it can carry a thermopile. You can consider this as a 1-pixel thermal camera. It can do contactless temperature measurement from the surface, and combined with tracking information, the robot can localize some abnormal, like overheating or overcooling spots on the surface. And it can carry a thermal camera to capture a heat map from the surface. And it can carry a visual camera to stream video from the area of interest, and we can do some detailed inspection. And about 3 years ago, we got the opportunity to work with a space technology company called Lunar Outpost to send one AstroAnt robot to the moon. And you can see here, the bigger rover called MAP-1 lunar rover is developed by the Lunar Outpost. They are sending their lunar rover to the lunar South Pole and can carry one AstroAnt robot. This is how the AstroAnt lunar version looks like. I actually brought a prototype. I learned this from Steve Jobs when he was trying to show how small the iPod is. Yeah, this is how the lunar version looks like. If you want to take a look. Sorry. And so you can see on the bottom of the AstroAnt, it also has a thermopile, can measure temperature from different positions. And notice on the top panel of the bigger rover, there is an aluminum box called garage. And inside the garage is the AstroAnt robot. The robot stays inside to get charged before deployment. And when we are ready to deploy the AstroAnt, we can send a command, the garage will open, and the AstroAnt will drive out, and it will be only working on the top panel of the MAP-1 rover. The top panel is the radiator of the bigger rover's thermal system. So it can capture temperature data from different positions of the radiator. We can use the data to help with monitoring the performance of the bigger rover's thermal system. And the AstroAnts went through a lot of tests to arrive at this flight-ready level for the lunar mission, including the vibration test to make sure the AstroAnt can survive under strong vibration during the rocket launch. And this TVAC test, or thermal vacuum test, we test the operation of the AstroAnt in a vacuum chamber. It's vacuum inside to simulate the vacuum environment on the lunar surface. And also the temperature inside the chamber is controlled to simulate the thermal condition on the moon. And this is the ground point test we did during the summer. This is the final test we did on the ground before the rocket launch. So point is between MIT in Cambridge and the lunar outpost in Colorado. We send command from MIT to Colorado, and lunar outpost relay the data to the rover, which is in their clean room, and the rover relayed the command to the AstroAnt to control its operation, and the data collected from the AstroAnt back to the rover and then to the lunar outpost control room, then back to MIT. So we did this test to make sure the ground communication links works perfectly. And this is how the whole mission looks like. Our AstroAnt robot will be carried by the MedPoint rover. MedPoint rover will be carried by the Intuitive Machines IM-2 lander. And the IM-2 lander will be carried by a SpaceX Falcon rocket. And 2 years ago, we already delivered the flight hardware of the AstroAnt. Now we're just waiting for the launch, which will be in the January of next year. Excuse me. This mission actually has a lot of meaningful impacts. First of all, although it's just a proof of concept, but it's still first of the kind of a payload. So through this mission, we hope to prove that for the future space exploration, we can use low-cost and miniature robotics to facilitate future space missions. And second, the AstroAnt is equipped with Bluetooth low-energy technology, which we have been using on Earth for many years. It's in your iPhone. And if we can get data from the AstroAnt, this can prove that we can just use off-the-shelf communication technology to facilitate future space missions, which can largely lower the cost. And it's a cheaper approach, can reduce human risk for inspection missions in space. It can also increase the repeatability of the data. And also, as far as I know, this is the smallest rover we have ever sent to the moon by human beings. And yeah, we cannot rule out aliens. And this mission has caught a lot of attention from the public media, including the Fast Company, Tech Briefs, Forbes, Astronomy, and also techie blogs and interesting engineering, etc., etc. So besides, other than the applications in space, this platform also has large potential on Earth, because the main purpose of this platform is using a swarm of tiny robots to access to some hard-to-reach confined space for human beings or traditional robotics platforms. Some example applications including the in-building HVAC pipelines inspections, and in the wild, maybe oil pipelines inspection, and also the inspection of the structure health of buildings or bridges, etc. So these are all the team members. Besides me, there's also Nathan, our software engineer, Toby, our firmware engineer, and Sean, our mission integrator, and my advisor, Professor Joe Paradiso, and the PI of the project, Dr. Ariel Akablo. So thank you.
If you look ahead for the terrestrial applications of this, do you have any concerns about the protection of the external surface from the environment?
Protected
from any external environmental influences? You were talking about applications for oil, gas, petrochemical.
Yeah.
Are there going to be gases or liquids that you need to protect that external surface from? And how do you see that changing behavior and functionality?
Oh, yes. So if I understand correctly, you mean the liquid might impact the operation of the robot? Yeah. So first of all, this robot currently using a magnetic field, so we need to make sure that the magnetic field may not be impacted by the the content in the pipelines, and also it might the design need to make sure that it might not cause problems to the pipelines. Maybe there's, for example, there's a leakage from a gas pipeline. We need to make sure that the design is good enough to not cause some problems because of the leakage. Yeah, currently is for the application on Earth. Currently, the design is really kind of rough, but we can upgrade the design based on the specific applications to make it as, for example, weatherproof or won't have interactions with the thing we're protecting.
Question here. What question?
For the terrestrial application, do you have a business plan as to what the cost is for making them? You're talking large scale, bigger numbers. So is there a plan that has already some numbers behind it?
Yeah. We are currently kind of having a plan to commercialize this platform, and the cost of each robot, actually the Model 1 and Model 2, is so cheap. It's like a 1 or 2 zeros less compared with the space version, a few hundreds tops. And yeah, for the I think if I don't know if I answered this question.
The business plan.
Yeah. So for the first step, we mainly focus on the infrastructure inspection because the bridges and also the buildings, they're made up of steel structure, which is very magnetic, and it's a good application platform for such a technology. So we first focused on this and use a special designed sensor to study the metal flaw to help with monitoring the health of the structure.
Yeah. Which is the operational temperature range, maximum and minimum temperatures where it can work okay?
What's the maximum and minimum temperature?
Yeah.
For the space, for the Model 1 and Model 2, the temperature is really limited, like minus 10 degree to like 85 degrees C, because I'm just using the off-the-shelf components, and the battery actually is the biggest problem because the temperature is too low. The internal resistance of the battery will be so high, and output voltage will be so low, cannot trigger the operation. And for the lunar version, it can work. We did freezer tests. It can work as low as minus 30 degrees C up to 85 degrees. It doesn't mean that when it's over this, when it's like out of this temperature range, it will die. It will still survive, but it won't trigger the operation. Like it won't start moving because the temperature is not that good for the motor or for the battery. Yeah.
One last question here.
Thank you. Again, back to the space applications. One would be the obstacles. I mean, if there's on a surface or so, if you have folds, if you have things that, how likely is it that it get bumped off and lost? And the other ones, when you have different failure modes on a spacecraft, how often are they fixable if you detect them? It's like in medical, if you diagnose something that you can't have a treatment for, then the question is, what is it good for?
Oh, thank you. First question is. First question is yeah. We tested it. Can there's a video show that it has this kind of tearings. We tested in microgravity environment. It can overcome this kind of obstacles up to plus minus 70 degrees on different materials. So it has this kind of obstacle overcoming capability. The second question is the failure. So currently we don't have a great way to. Detecting where the problem is might be very important, and currently we don't have a way to. For the robot, it doesn't have a way to repair because that would need extra, like a bigger, more sophisticated payload. So normally for repairment, we would normally rely on the robotic arm and a human astronaut. And for the failure of the robots, currently we don't have a great plan to recover it from a flip. For example, the magnets we use, the attachment is much stronger on the side compared with on the bottom. So if it flips, then it's hard to recover it from to the nominal orientation. currently it's one of the biggest problems we are trying to solve, because we are looking for some other attachment approaches.
Thank you.
Thank you.